Okay, so we're working on the root test today. And in order to get to that, we have to get to an idea called absolute convergence. Okay, so when you have absolute convergence, what this means is that if I have the series and I actually take the absolute value of an and it converges, then I have absolute convergence. Okay, so if the series converges and the absolute value of the an, the series of that, diverges, then we say that we are converging conditionally. Okay. So this begs the question about, like, well, what if it's the other way? What if the absolute value converges, but the series diverges? Well, that's not possible. We actually have a theorem that says that if an converges absolutely, then an has to converge. So absolute convergence implies convergence, but convergence does not imply absolute convergence. And if you have convergence without absolute convergence, it's called conditional convergence. Okay, so like absolute convergence is way better because it tells me that not only do I have the convergence of the absolute values, but I also have convergence of the original sequence itself. Okay, so we have two tests that talk about absolute convergence, and we're going to go through one in this section, and then we'll go through one in the next. Okay, so the test that we're looking at today is what is called the root test. Okay, ROOT. So in this test, you end up taking the limit as n approaches infinity of the nth root of the absolute value of a sub n, and then we're going to compare this to 1. So it's either going to be less than 1, this limit may be greater than 1, or this limit could be equal to 1. If it's less than 1, this tells me that the series an converges absolutely. So if I take the limit of this root and it's less than 1, I get absolute convergence. If it's greater than 1, I get divergence. And if it's equal to 1, the test is inconclusive. So I've got to try something else. So the root test is pretty good. What it will do is it will take a situation where you have something to the power of n. It'll allow you to strip that nth power off and tell you whether or not the series converges absolutely or diverges. Occasionally you'll get this like it's going to 1, but then you have to try to find another method to determine convergence or divergence. So let's work an example of the root test. So let's say I have the series of 2n plus 3 over 3n plus 2, and I'm taking that to the nth, right? So I want to take the limit as n approaches infinity. Notice what makes this tricky is like the inside of this thing is going to 2/3, right? But if I take that 2/3 to the nth power, that seems to be going like off to infinity, right? Or actually down to 0, right? So this is like a strange little bit here. It's like, what does this converge? Doesn't it? Is it? Who knows? All right, so let's take a look. If I do this and I take the nth root of the absolute value of 2n plus 3 over 3n plus 2, right? This is going to be the limit, to the nth. So it's that to the nth. Well, this is all positive, so the absolute value doesn't matter in this case, right? So the nth root and the nth power come off, right? So this is going to give me 2n plus 3 over 3n plus 2. That limit goes to 2/3. That's strictly less than 1. So this tells me that this series converges absolutely. Okay. If this had come out as greater than 1, I would say that it diverges. And if it came out as equal to 1, then it's inconclusive, and I have to use some method other than the root test to be able to find convergence versus divergence. All right, so there you go. Absolute convergence, conditional convergence, and the root test.